Okay, great. So yeah, thank you, Rama, and thank you, DataPhilly organizers for the opportunity to speak. And welcome everyone to our presentation about people analytics and predicting employee attrition. So I'm Ben Attix. I am a data science consultant at Slalom. I've been at Slalom for 2 years and working as a data scientist for 3 years. And I'm joined by my colleague.
Hi everyone. I'm Andrew Garfinkel. I'm a data discovery and visualization consultant at Slalom, born and raised in Philadelphia, and I've been at Slalom in Philly for the last 3 years
now. So today we're going to talk about first, what is people analytics? What do we mean by that? Then we're going to talk about some ethics in people analytics, then an employee attrition use case, and then an automated training pipeline and attrition dashboard. So just as all organizations are becoming more data-driven, business units like HR are becoming more data-driven as well. And so what people analytics means is that it means using data to help organizations uncover new insights about their people, solve people problems, and direct actions. Employees are the asset we have here, and asset's probably even the wrong word to use, but because we were talking about people as assets, but employees are the most valuable part of any company. And so it's up to HR and organizations to make sure that they're maximizing their talent and helping their talent succeed as much as possible. So with more data that they have now, HR and organizations can use that data to make better decisions, and decisions across all aspects of the employee lifecycle. So whether that's recruitment at the beginning of an employee lifecycle, through maybe onboarding, professional development, promotions, and retention at the end of the lifecycle. And it's about not just getting insights, but also being able to take action on them. And so the reason people analytics is gaining momentum is because it's cost-centric, it's measurable, tangible, and it represents for most companies their largest cost, which is the cost of their employees. And so, so a study of exit interviews of over 200,000 exit interviews found that 77% of employees who quit could have been retained. And that's a huge number. And so, organizations are doing what they can now to try to understand why people are leaving and what they can do to help improve the employee experience so that now your employees are happier, they want to stay, and then that's helping you ultimately with your retention. So it's really a win-win, right? The employee experience becomes better, and employees become happier, and then they want to stay. It costs upwards of 150% of annual salary to replace a mid-level employee. And so this is really expensive, right? And so that's why, or one of the reasons why companies want to make sure that they're retaining their talent. And profits increase by 49% when high performers stay in management roles. So again, your top talent is very beneficial for you. And so you want to do what you can to keep your high performers with your company. So before we get any further, I think it's important to talk a little bit about how bias might influence development of people analytics solutions, or more generally, some ethics around people analytics. This is the ethics topic alone is something we could spend a few hours on, and obviously we don't have that much time. But I think it's important to at least address some of the high-level topics or high-level ideas, but just know that there's obviously a lot more depth underneath this that we're not going to be able to get to today. So bias in people analytics. Bias is important in any data science project, right? As data scientists, we talk about bias in our models, but when you're dealing with people data, there are many other bias concerns as well. And so here are just 4 that we've listed, but there are many others as well. So the first one, bias in problem definition. How are the problems being defined? Who's coming up with the use cases? Number 2, bias in data. Is your model biased by historical data? If your historical data has any bias and you're building a model off of it, the model will just perpetuate those and continue with those biases. An example of this is Amazon built an algorithm to vet applicants' resumes over using 10 years of historical data. And most of those resumes over that 10-year period happened to be from men because it reflected the male dominance in the tech industry. And so then in effect, Amazon's system taught itself to prefer male candidates, and it started penalizing resumes that had included the word women, like a women's club captain, and also penalized resumes that had of people who were graduates of all women's colleges. And so, yeah, as you can see, that's obviously a really bad effect, and it's something that's caused by the bias in the data. Now, Amazon ultimately realized this and like decommissioned the model. They're not using that anymore, but it's just something to always be aware of in projects like this. Number 3, bias in design. Are models being used for unethical purposes? Is the technology doing something it shouldn't do? And 4, bias in application. Does the person interpreting the data demonstrate bias? So with people analytics solutions, you don't want to automate any actions or have the output of an algorithm like making decisions. That should always be fed back to a human. And so, you know, in this step, even if the model itself shows absolutely no bias, you know, it's being fed back to a human. Does that human introduce bias? Is something to be aware of as well. So here are a few principles for accountable algorithms. And the key point is that algorithms and the data that drive them are designed and created by us, by people. And what that means is like we can't hide behind saying, oh, well, the algorithm did it, or, you know, it's the model's fault. Ultimately, we as the people who create and design them, we need to be responsible. So that's the first principle. And then the model needs to be explainable. You need to be able to explain in non-technical terms why it's making any predictions that it is. It should be accurate, and you should know what is the margin of error on your predictions, where are errors more prevalent, and can errors be mitigated? And it should be auditable. So you should be able to probe and review the behavior of the algorithm. You should have documentation for the algorithm. And finally, they should be fair. So you should ensure that it's not creating any unjust impacts across different demographics, whether that's race or gender or age, for example. And then 2 quotes that I thought were really kind of impactful on this topic too is the first by David Green, who is a people analytics thought leader. He says, people analytics leaders will continually be faced with the dilemma of what they could do versus what they should do. Perhaps the best test is this: if you cannot articulate the benefit to the employee as to why their data should be collected and analyzed, then the project simply shouldn't be undertaken. And this goes to what I was kind of saying earlier, like it should benefit the employees as well as benefiting the company. So it should be a win-win. And then Tom Davenport says, if you learn from an AI system that a job candidate is likely to perform well, or that an employee is likely to leave the company, the next step is not an automated action, but rather human intervention. Again, like I was saying earlier, you always want a human in the loop, and you know these algorithms should not be making decisions about your workforce on their own. So with that said, let's talk about a specific use case about employee attrition. So I kind of talked about the attrition a little bit before, but just to summarize the problem is that if you can predict the probability of an employee leaving and then identify the most likely risk drivers for why they might be likely to leave, then you can take action to prevent and minimize the impact of attrition. And these actions are things that, again, improve the employee experience so that your employees are now happier, they want to stay at the company, and everyone benefits. So at Slalom, we had a client who had experienced significant attrition in their warehouses as well as their IT organization. And you know, we had determined that they would have $1.5 million in annual savings from preventing attrition. And that's just for the warehouse and IT organizations. If they scale that to the rest of their business, the savings would be 10 times that much. So like this is a huge number. And as I was kind of saying before, with like people analytics being really measurable, it's when companies see this impact and they're able to quickly calculate the ROI, it makes them more likely to embark on a data science project like that when they know what the return is going to be. So going into some more of the details, this is the data architecture that was implemented. So data was pulled out of Workday. If you're not familiar, Workday is an HR management system. And so data was pulled from there and then it was ingested into Microsoft Azure, where some pre-processing was done, and then it was sent to an ML blob. When it hit the blob, it triggered an ML pipeline for training and retraining. And part of that pipeline was then executing an Azure AutoML model. I'll talk a little bit more about this model on the next slide. And then once the model is trained, it's then fed to a pipeline for scoring and for outputs. So, to evaluate, okay, how well is this model performing, as well as looking at some other metrics for explainability. And I'll go into details on that on the next slide as well. And once we have that output fed back through some of the different systems, ultimately reported out through Power BI, where the HR organization could look at it. Obviously, HR is going to be the ones kind of making decisions. They need to make sense of this. They're not going to have any understanding of any of the data science components throughout. So it's important for them to have some tool that they can use, play around with, and understand the data. And then from there, they can determine what actions they're going to take, whether it's talking to someone's manager, reviewing someone's compensation, reviewing their ability to work from home or not, for example. So some of the modeling considerations that we took, as I think briefly mentioned, there was automated monthly retraining to help with model drift. So every month, a new data extract is loaded into Azure, which then kicks off all of the processes that I showed on the last slide. And so if any factors become more or less important over time, the automated retraining, the retraining of the model should help avoid any, or keep the model up to date. And Azure AutoML was used to pick the best tree-based model. So Azure AutoML there's a bunch of different configurations you can do with it. Some of those are like constraints you can put around it. So for this project, we put around constraints to say only use tree-based models. The reason we did this is so that we could use SHAP values for interpretability. SHAP values are only available for tree-based models. And if you're not familiar with SHAP values, what they do is they can show you how much each predictor contributes either positively or negatively to the target variable. So the target here being attrition. And each observation, or here each employee, they get their own set of SHAP values. So for one employee, you could say their overtime makes them more likely to leave, but for another employee, you could say their overtime makes them less likely to leave, the amount of overtime they're working. And it tells you not just direction, positive or negative, but also the magnitude, so you can understand which factors are more important than others. And then overall, some factors that we found were important over the entire employee population was like time in position, time with the company, performance ratings, base pay. And then attrition here we defined as an employee leaving at any point in the next 12 months. You have to set some kind of time box for what you determine as someone leaving or attriting. So if someone left 5 years from now, you wouldn't say that they're like high risk to leave now. So anyways, you have to put some constraints or time box around that. So we use 12 months. And then based off our experience, like some advice or recommendations we would give if you were looking to embark on a similar project at your organization. First is adverse impact analysis, which is really fundamental to people analytics projects, like any people analytics projects, not just attrition. And this is the analysis of negative effects that an unfair and biased selection procedure has on a protected class. And so you could look at like anywhere where there's a selection process. So like any of your hiring decisions, promotion decisions, or here decisions that you might make to retain somebody, and look if there's any adverse impacts. And also you should be looking both pre-model and post-model. So what I mean by that is even before you embark on creating any model here, you should be looking at, based off the organization's current behavior, current decision-making process, are there any biases? Are there any adverse impacts? And if there are, obviously take measures to mitigate those, as well as make sure that they're not working their way into the model and creating further problems. And then you also want to look post-model. So once you create a model, you want to make sure you're heavily investigating and looking at the outputs, making sure you're not introducing any adverse impacts at that point. So for example, if the 10 employees who the model's deemed to be most likely to leave the company are all men, then it would not be a good idea to simply say, okay, well, we're just going to increase all their pay, because then you're creating adverse impacts. Number two, like working with the business. So you should have a clear understanding of which business unit owns and maintains the model, as well as align on expectations and outputs. So there'll probably be a lot of different business units involved. Obviously, HR will be involved. Yourself, like the data science team, would be involved. You'd probably have IT, any business units that you're working with for their specific attrition problem. You might also have data engineers, software engineers, maybe data visualization. So you have to make sure that everyone is on the same page about where everyone's role begins and ends, and what the outputs will be. And then as well, spend time on end user training. So for our project, I mentioned the end users was HR. And so they need to, and the end product was like a dashboard. So the HR needs to understand like how to use that dashboard. They need to understand how to filter. They need to understand like how to navigate. And they also need to understand anything that's in there. So earlier I mentioned SHAP values. If that's something that's going to be in the dashboard, HR is going to have no idea what a SHAP value is. So you need to make sure that you're teaching them what that is, what it means, how to interpret it. And then the last one, data. So data quality is key. I mean, it's really key in any data science project, but especially when you're dealing with people data. And then some other data that can help is pre-employment surveys can be helpful. Employee engagement surveys can be helpful. Exit interviews can help inform you where you should look. So if you're having exit interviews with people, that there are companies having exit interviews with people that keep saying they don't see any room for career growth, well, you can design employee engagement surveys around that to ask your current employees, like, do they feel that they're not getting enough growth? What kind of growth would they like? What else can you do to support them to, again, make their employee experience better so that they would want to stay? And also, as your employees are growing, they're going to be being more profitable, beneficial to the company. So win-win. And Likert scales better than binary variables. Just kind of found the more levels you have can be better. So with that, I'll pass it off to Andrew.
Yeah, thanks, Ben. Ben, thumbs up if you can hear me.
Gotcha.
Yep, great. So today I'm going to talk about an internal project that I worked on where we took sample mock data and we built an attrition model. And then we visualized the outputs in dashboards. And in building the attrition model, we also built an automated training pipeline in AWS. You go to the next slide.
Yeah.
So for a bit of background, in January, I was given the opportunity to pursue a passion project. And so one thing I was really interested in is how do we take these advanced analytics or machine learning model outputs and visualize them in really intuitive, business-friendly ways. I was working with a consultant in London at the time, and he was really interested in how do we actually get ML models to production? So how do we move beyond that Jupyter Notebook stage and actually get them operational in production? So after talking to each other, we were both interested in the attrition model use case. We were able to find really good sample data on Kaggle, And we thought that would be a great way for us to prove out the concepts there and build out some dashboards in the automated training pipeline. So for today, I'm going to walk through what that automated training pipeline is, the infrastructure, or the code that actually underlies that infrastructure. We made open source, so if anybody wants to access it, they can. And then we'll finish off by going through some of the dashboards that we built. And the consultant from London was going to join, but it's almost midnight there, so I'm taking it over for both of us, but I can speak to all of this. So I wanted to go through the overall requirements for the attrition model, and this is how we thought about the attrition model, the model component of this project. So first, we knew we needed some sort of transformation job. Whenever you're doing anything with data, you almost always have to transform it. Next, we wanted to predict the risk of an employee leaving, so we viewed that as a binary classification problem. But we thought, predicting the risk isn't enough. If you know that someone is likely to leave, there's not a lot that you can do with that. You really need to know why they're going to leave. So we really wanted to make the outputs interpretable and also be able to visualize that. For the actual model itself, we really wanted to automate the retraining process. So again, making this more of an operational model as opposed to something that just exists in a notebook. We weren't worried about a persistent endpoint. We knew we were going to do batch inference where we just drop a file. And we wanted a way to easily update the hyperparameters. So if we go to the next slide, here are the model details. So for the second requirement around that binary classification model, we went with an open source XGBoost model. And then for the third requirement around how do we actually make that interpretable, we went with that SHAP library. And with that, you can actually just pass the XGBoost model object into SHAP, and it will generate a SHAP value for every employee and every variable. And as Ben said, it will say not only the direction of whether that contributed to the attrition risk or it did not contribute, but it also gives you a sense for the magnitude. So moving on, I'm now going to walk through the attrition model pipeline, but all of this was built using Terraform. So Terraform is infrastructure as code. For those familiar with AWS, it's similar to AWS CloudFormation. So if you are interested in this, I will include the link to the GitHub where all of this code exists. We don't actually have the model code there, but we have this code for this whole pipeline. So if you have an AWS environment, you can run all of the Terraform code and it will actually spin up all of these different services and deploy them. So walking through this model itself, we have our feature store, and that's just where we store our base data in AWS 3. And then the automated model pipeline, you can see in the pink box. So we used AWS step functions, which are just a way of orchestrating different AWS services. So stitching together different services. We used AWS Glue for our data extraction job. From there, we passed that into SageMaker. The original intent was to use one of the built-in SageMaker training algorithms. The issue that we ran into is most of these behave pretty much like black boxes. So they'll give you a prediction, but you can't tell what's going on. And you also can't pass those into the SHAP model. So we had to get creative here, and we used the bring your own model approach. So what we did is we used Amazon ECR, which is just a container service. And we had a model image for both SHAP and XGBoost. And we imported that into SageMaker. And then that's where we had our model training, tuning, and evaluation. And then we used step functions again to actually do model validation to understand, is this accurate? If it is accurate past a certain threshold, let's use it. If not, then let's not. So from there, we have our model inference, and that's actually the scoring. And all of the output was written to an Amazon S3 bucket. We used the glue crawler just to identify the schema. And then we used Amazon Athena, which is just a way that you can write SQL query against data that's in an S3 bucket to ultimately get the data into Tableau, which we use to visualize the output. So if you look on the bottom left, you see that AWS Lambda trigger. That's just a way of writing serverless code where now whenever any new training data is dropped in the relevant S3 bucket, it will trigger all of these services to run. So that's where you get the kind of automated part of this pipeline, where whenever you do want to retrain the model, you can just drop new data in, it will trigger the Lambda function, and all of these services will run. So if you go to the next, this is just more detail on how you can actually leverage this if you are interested. This doesn't have to be used for attrition. If you look at the pipeline, it's pretty similar to, I think, a lot of other ML and data science problems. So I will ping these links within the chat, but this is overall Slalom's infrastructure catalog where we have all of these Terraform modules. So now I'll walk through the actual dashboard. So if we go to the next page, the kind of overarching theme with this was we wanted to make it really simple and easy for a business user to understand. And so the way I went about structuring this problem is let's just break it down into 3 really simple questions. The first is what did happen? And that is purely historical. So it's not looking at anything predictive. It's just what happened with attrition in the last year. The next is predictive, and this is more of that kind of XGBoost output about what will happen, overall, who's likely to leave. And then finally, this is where we get more to SHAP and interpretability. Why will it happen? So why are they likely to leave? And most importantly, what are some actions that you can take? So walking through, this is a screenshot of the historical dashboard. You can quickly see what your historical attrition rate is. You can also see characteristics that are associated with both high and low attrition. So for example, sales representatives, it's almost 40%. Research directors, it's about 2.5%. So both high and low. Monthly income bin, if it's a very high income, you have low attrition. But all of these dashboards you can click into, and we really wanted to enable business end users to have some data discovery. So if we go to the next slide, this would simulate you clicking into job role. So on the top right, it really spells out what are the highest feature values, what are the lowest feature values for attrition. And then it also breaks down that feature value itself. So if you look, it shows all of the job roles, and you can see that human resources has a high attrition rate, lab technician has a high attrition rate. So again, it's kind of an exploratory dashboard, gives you rear view what happened in the past, lets you click around, and it kind of anchors you to before you get into something more predictive. If you look on the top left, you will see that there are still 1,233 retained employees. So that will bring us to the next dashboard. And this is saying, okay, for these employees that you retained, who are likely to leave? So which groups of employees represent the greatest attrition risk? And also departmentally, where is that in your org? Maybe there's a lot of risk in sales or HR or for a certain job role. So you can quickly see that based on this, and again, this is all mock Kaggle data, there are 40 employees that are high risk. On the right, we have the distribution. So you can see when we say high risk, is that 40 employees that are in a 95, or is that more employees that are in the 65 to 70 range? If you look on the bottom right, you start to get global feature importance. So for all of these employees, what are those key feature value pairs? Is it they worked overtime, or maybe they have bad work-life balance, or they travel a lot? And then on the right, on the bottom left, you have the department that you can also click into and view job role. The real goal of this dashboard is that you can click around and see different employee groups, but it's to help you get to a smaller employee group that then you can really drill into. So in this case, if you click into sales and you see there are 3 really high risk employees, there is that view group attrition risk that has the blue underline. So simulating clicking into that, that will then finally bring you to the why will it happen dashboard that really starts to get to what are the main drivers of risk score and what are some actions that you can take. So for this group, what you can see is what is the group score? And in this case, for these 3 employees, it's close to 70%. And then you can see the main factors that are actually contributing to that. So it's overtime, business travel, and their overall environment satisfaction. All of those features on the left, you could then click into to see, okay, how many of these employees are working overtime, how many are actually traveling. But the goal here is that you can also click to the individual employee level. In some cases, you know, some orgs would be okay with people in HR seeing that. Others would only want it at the group. But if we go to the next slide, this will simulate, let's click into employee 573. And for them, the main contributors to risk are business travel, distance from home, that is, you can't see the label, but that's underneath there, and stock option level. And then from there, we just suggest some next best actions. In this case, next best actions, that is not an ML model. That is just essentially coding saying, if this is a high risk score for business travel, then do this. So some examples of actions here is if it's business travel, maybe let's look at a non-travel role, or if it's distance from home, let's look at and explore a work from home option. All of this was built in February when these were still things that not everyone did. But the one thing I want to point out is that if you look at these next best actions, they're not telling you to do something. They're really saying, look further into something. these are starting points for you to start asking kind of more intelligent questions, for you to go and dive in and do some more research about how you can improve the employee experience for one of these employees, and hopefully take some sort of action to retain them or to retain a broader group of employees.
Great.
So,
yeah, thanks, Andrew. So that's all we got. So open it up to questions.
All right, thank you so much. That was really interesting, Ben and Andrew. So we had a couple of questions that came in through the chat, and a couple about the retraining part of the slides, and what type of features, Eugene wanted to know, what type of features did the attrition model use, if it's not a secret?
If it's not what?
If it's not a secret, if you're allowed to reveal features.
Sure. So yeah, some of the data that was used is like some of the data that Andrew was showing you before, right? So how much business travel, how much overtime, also looking at like performance ratings, pay rates, what business group they're in, have they had a change in their manager recently? So those are some examples.
Okay, thank you. Yeah, I saw some of those in the mock data, but I don't know if there was something different that was used for the use case that was given before. Okay.
They were pretty similar.
Pretty similar. Okay, and then Carl wanted to know, did you add new data to the training set, or like using a 90-day rolling set of data, or how did you do that?
So I guess each month kicked off the retraining, and so at the end of that month, you'll know some more information about who left, obviously, and then you'll also have more information about like, did anyone have changes in their manager? Did anyone's performance ratings change, or has their overtime changed? So it's looking at like changes like that and feeding in essentially concatenating or just appending new rows.
Okay, and then there was a question about the ethics of the data collection. So Rama wanted to know, do the employees know that their data is being used for this purpose?
Yeah, that's a great question. So I was only working tangentially with this project and actually not directly with the client. So I'm not sure, but I believe that they were, that the employees were aware of it, but okay. I'm not positive about that.
All right. And then the last question, well, one more question here is regarding the model. Does it consider the underlying distribution of the variables?
I'm sorry, can you say it one more time?
Does the model consider the underlying distribution of the variables? And I might have Cassil explain this question a bit more in case I'm...
Yeah, do you mind elaborating, whoever asked the question?
Let me see, I'm trying to go unmute. So when we have the independent, I understand that you're considering a binary dependent variable, but for the independent variable, when you talk about the transformations or other things, you know, what kind of underlying distribution does it assume? Do you default it to the software to decide, or is there any kind of visualization that you consider looking at, you know, the relationship of the dependent to the independent variables?
Yeah, it's a good question. I don't believe there was consideration for the underlying distribution. I think it was because there's a tree-based model, the distributions usually aren't as important for tree-based, or I shouldn't say they're not important, but they don't really affect how the tree-based model would work. So I don't think it was considered.
Okay, okay. Yeah, I guess tree-based models are a little different. So it doesn't also impact any kind of multicollinearity because you're putting all the variables together and letting the model sort of decide how to prune that.
Right, and it also, because tree-based models work based off split points, like splitting the data and then everything to the left, it does one thing, everything to the right, it does something else.
Yeah, like
it doesn't assume like a normal distribution or anything like that.
Yeah, yeah. I think it probably does chi-square, like shade models, yeah. Okay, thank you very much.
Yep.
Okay, Thank you for clarifying that question. Carl wanted to know, do you check for model drift or data drift? And can you discuss your hyperparameter tuning?
Yeah, so the automated training of the pipeline was kind of designed to address that drift. So like if different factors become more or less relevant over time, then the retraining of that will help with the drift. And then, sorry, what was the second part again?
Can you discuss your hyperparameter tuning, just in brief?
Yeah, so this was, it was mainly, in this project, it was done by the Azure AutoML. So that was really the reason, that was really the only thing that the AutoML was doing, was kind of like just automating the hyperparameter tuning of the model.
Okay, thank you. And then the last question before we move on to the next speaker event is, what is the positive predictive value of the model, the PPV or sensitivity of the model? This is from Ramon.
Right. So I think I can have something here. Need to look that up. So I'm not sure exactly about the PPV. The area under the curve, the ROC AUC was 0.91. So that was one of that's the only accuracy metric I have in front of me right now.
Awesome, thank you. So this was really interesting, and anyone else, if you come up with any questions, we can go into them at the end of the second speaker event. But thank you so much for your talk. It was really interesting.
Yeah, thank you.
Yes, thank you for the opportunity.
Thank you. All right, so at this point, I'll hand over to Michael Bolden. If you want to start sharing your screen, that's for our second speaker event.
I hope it's showing now. Yes? Yes.
Yep, I can see it. Thank you.
Okay. I'm going to pre-apologize. I have a laptop off for repair, and I'm going to tell you, never send your laptop for repair during a pandemic, because no one has any idea where my laptop is. So this is somewhat a new system I'm trying to work on, so I might have some glitches, but thank you for having me. And you can guess by the topic that this is something that I've only recently started to do any research on. I've studied for a while business cycles and how you look at the economy and using data science, looking at the economy. And during this project, I'm really learning about both COVID data, how epidemiologists look at pandemics and things like that. A little bit myself, I teach at Temple in the Department of Statistical Science. I teach both our undergrads, what we would call SSDA, which is really data science for undergrads, and we have a master's program as well. And I guess depending on some of the feedback, I might have some of my students look at some of the numbers and information I'm going to show now. The last thing to say, and just to start, is I'm going to put almost everything up on GitHub. If you want to see the data I'm using, programming I'm using, and such not, that'll be available and to both use or contribute and give me some ideas. But again, this is all in, oh, I didn't do this right. I have something wrong. Give me one more second. There we go. Closer to be able to go. So the project is really, how do we know we're in a recovery? I'll talk about the definition of business that economists use. But just to start out, the dating of when we went into recession would be the month of March. And officially, this was the fastest that the group that decides recession has ever reported that we're in recession. Usually they wait till a recession ends before they even say the recession began. There's a lot of things that are different in this case. The data is actually quite unique. I'm going to show you some charts. And for people who look at time series data, almost everything since March looks like an outlier. And so that causes all kind of havoc in modeling and handling data. The second part is just a personal belief. I don't think we'll come close to what you'll call a recovery or feel recovery until the public starts to feel comfortable. And I'm going to believe this is really going to come on a county by county basis. We all hear in the news how they'll report that some states are doing very poorly, My wish is they'd really just concentrate more on areas or counties that are in bad shape. I know stories of people tried to travel different parts of the country, and they can get stopped based on their license plate that this state has a high hit rate for COVID, and it really should be more at the county level, but it's just too hard to do. I did it wrong again, sorry. There we go. There's a whole host of data. I won't spend much time on this. It's almost much data for someone who's not familiar with economic data to digest at once. Just to know that there are only estimates that come out when we look at how the economy is doing. The most popular one on Wall Street is called payroll employment. That's the first bullet point there. You also hear the unemployment rate. That's the second bullet point. And this comes from the current population survey. And these two surveys that I'm mentioning here, the payroll one is all by a factor 100 larger than the household survey. But the best data, I think, to look at right now is something called unemployment claims. And I'll show a graphic of that. And others, I'll just let you just read those quickly. If I do have time, I'll show you also the FRED system coming out of the Federal Reserve Bank of St. Louis. And they have ways to, they've amalgamated all type of data, and they will have ways that you can download and put together. And I suggest if you want to get this economic data to use Panda's data reader, and they have an API that's very easy to use. Okay, this is a picture, we get first picture of outliers. This is the unemployment rate. Economists like to draw these gray shadings to talk about periods of recession or downturn. This is the unemployment rate. It's going to rise when the economy is doing worse. And so in the gray periods, it's rising. It doesn't hit exactly its peaks and troughs exactly in the gray period. And you'll just see that the unemployment rate went over 15%. Not any time in my lifetime has ever been an experience like that. It went from 4 to over 15%. It's declined since then. And the question could be, does that mean the recession is over, given the unemployment rate has started to decline? This is I believe is probably the best series right now to look at the economy. One, it's timely, and the second is not coming from a survey. These are the claims initially for those that are claiming layoff and getting unemployment insurance. So until we hit 2020, the numbers were less than 200,000 per every week. And that's what people would say is we expect the economy performing well to be roughly 200,000 new claims to receive unemployment insurance. And here's the outlier picture. This is if you put in just the month of March. It goes over 7 million. These are actually the same lines. These lines right here, if I can draw. I won't bother drawing right now. But you'll see these are actually the exact same lines being shown. And that's just a great outlier, something hard to deal with. We're still way over by a factor of 5 of the 200,000 that you might consider normal times for the economy. So layoffs are high, unemployment claims are high. It's taking a real toll on state budgets and so forth. This is somewhat trying to put the unemployment numbers as an unemployment rate and these insurance claims onto the same footing. And here I'll talk a little about, how to transform data. So the blue line is the unemployment rate in 2020, and we see it rising over 15%, and it's fallen since then. The yellow line is not initial claims, but continuing claims, those that are still receiving their weekly employment insurance checks as divided by the labor force. And you'll see in the earlier period here, and this has been historically true, that the actual number of people receiving unemployment claims is only a small fraction of those that tell us they are unemployed. But in recent times, it's actually reversed. We have more, or roughly the same amount of people telling the government they're unemployed through the household survey as those that are asking for claims. And this is the sort of the new or the change part. So these are new claims, and these are those that are continuing. And so we have this unique feature where roughly what the surveys say is unemployed is the same as the amount of people that are asking for unemployment. So again, it's these unusual numbers going to be hard to fit in any type of data framework if you're going to use history as your guide, because we're into new things. So I'll cover some things. I'll give some advice of just doing general data science to a research project like this. I'll explain somewhat how the economics profession looks at business cycles, and I'll try to do this from the more general academic economists versus Wall Street economists. They really mostly care about stocks going up or not, or what's happening with the bond market. I'll also look at both how economic data and publicly available COVID data may move together, and maybe I'll use the Johns Hopkins set for the second part here. And then I'll talk about some preliminary ideas. And one of my points will just be, I think, to understand what's going on, it's important not to look at things from a national level, but the state or possibly level was even wrong as well. And then again, I'm taking any suggestions because this is work in progress, just getting started. And then I'll just talk a little bit, incite some theoretical models. So I have a colleague, I'm working with Mark Sobel. He's helping a lot, or giving me a lot of guidance on doing some Bayesian perspectives and something called a Dirichlet clustering Dirichlet process, which is a more complicated statistical technique. And then if I had more time to talk, I'd do some of these other ones here, including looking at nitty-gritty of data, other research by others, the more about this clustering and Bayesian part. And I could probably spend 20 minutes ranting on how the government is really letting us down, but not reporting sufficient data and timely data. And where the quick part would be, I can get COVID data from yesterday. I cannot get employment data to look at for maybe 6 weeks to after it's been gathered, and in some cases 6 months, which is actually, we could actually do a lot better to understand the economy if actually things are done much more reasonable standpoint than the government certainly gathers the statistics. So this is the picture I'm sure most people have seen. It comes from a gentleman, Stephen Colossus. And it looks like it can explain how do you apply different tools to solving a project that needs data science. We're going to need communication. We're going to need, I would put in here math and statistics. I would put in here both data management and programming. He has business here, and we might want to just put area expertise. And this is a contrast to what maybe many would say the more popular Venn diagram coming from Drew Conway. He just had 3 diagrams, 3 things. He used the words hacking, which I don't like. I want to think about true program, true coding, and good data management. So I do have some advice. If you're doing a project like this, it's important to gather the data and handle it well. And I know from experience that even the best intentions, if you do bad data management, you can ruin a good project. What I tell my students is sort of a joke here, is I do ask them to try to learn 2 programming languages. And I will talk about using both, or I've used for this project, both Python and Excel. If I had done this 15 years ago, I might have been using SAS and MATLAB. I like the open source free ones. And then the joke is that Excel is not one of these languages that we should allow to enter our work or be important in putting things together. My students often want to fall back into Excel. Then you should have some area expertise and think about the theory. I have a lot of experience with the economics data, and I'll show you some of the theory about the pandemic that might help us understand things and understand where our data is limited. And then what you want to do is apply that and find those I call the sweet spot, somewhere between don't be overly simple and don't overfit at the same time. And here you have to think hard about how your data fits in mathematically and statistical methods. And then data visualization helps at all stages. I'll show a lot of pictures. I don't put a lot of time into making them pretty, but I do think they're helpful to communicate some of the things going on. And it's really easiest to show outliers. For example, the graphs I showed already. So let me first start about, if we want to talk about when this recession ends, we're going to start first with, well, we have to know how do economists think of dating recessions. And usually they're looking for peaks and troughs in the economy. And one people do use is a GDP 2-quarter rule, which would be if GDP falls 2 quarters, we're in a recession. That is not what's really done. There's also unemployment rate rules. There's also coincident index rules and there are other rules. The official way is through a committee in Cambridge, Massachusetts, National Bureau of Economic Research. They have probably 8 members right now. They vote. And there is no formal rules of how they decide peaks and troughs. They're looking at a whole slew of information when they pick these dates. And there are some modeling ways to do it as well. And you can think of, even though this committee is informal in how they come up with their peaks and troughs, you could potentially model them by using things like dynamic factor models. I will show a dynamic factor model results that I've run. More complicated, use switching models, and then you can combine factors and switching, if that's what you like to do. This is the dynamic factor model. I'm just gonna go briefly over this. Probably too much to go into the ghetto of all the notation, but to think about it here, there is something running the economy that's pushing the economy on what is called a C. It's a common factor. It's completely unobserved. And our job as data scientists or econometricians is to figure this out from the data. Apply some technique that figures out this common factor that's driving everything. And so we're going to assume it's normally distributed, has a 0 mean, and just for identification purposes, we'll set its variation or variance at 1. And then you can measure actually numbers. So we can have a whole slew of indicators, 1 to K. I'll show 4 indicators, I'll fit something. And we'll say these are being driven by this common factor. So we're going to use these 4 sets of data, time series of data, and try to figure out this C. And again, this is going to be normally distributed for tractability, and it's going to have its own variance and covariance. And how you would estimate this, I won't spend any time in details of the Kalman filter. Kalman filter is perfect for this application, very efficient, and you can do maximum likelihood estimation or potentially EM algorithm, Bayesian algorithms, all type of things. And so I'm going to show results by using a Python module, stats models, and the dynamic factor method. And so that comes out next here. This is the 4 series that I'm looking at. So employment, this is the payroll employment I talked about at the beginning. It's very smooth. It's one that people probably follow the most to looking at cycles in the data. Second would be industrial production. This is not the total economy. It's probably only about 30% of the economy. And none of these are going to be GDP, which might be more popular to talk about on the news, but people want to date the business cycle on a month-by-month basis, and GDP comes out quarterly. So the 3rd series would be income, and the 4th would be some measure of sales. You can see some commonality here. So the job of the Kalman filter and maximum likelihood is to look at these 4 series and figure out their commonality. Your first step, though, was to normalize them in some way. We don't like the numbers that trend upward. They're not stationary. They're not going to fit into a model well. We need to normalize them here. So here I fit everything to have a 0 mean. These are log differences. Here's the employment number. Here's the industrial production. Here's the income numbers. Here are the sales numbers. And you can see that there's potentially less information as we go from this quadrant to this quadrant to this quadrant to this quadrant. And these have on their own outliers potentially you might want to control for. And sales you might think is mostly noise. It's not going to help us at all. But we can take these 4 numbers and produce something that looks like this. This finds this common factor. And here it looks to do a pretty good job of hitting the gray areas of when the MBR committee said we were in a recession. So I haven't shown in 2020 yet. So this is just how it works before. If I had not known anything about COVID and I had done a study in the beginning of the year, I'd get numbers like this. And this green line is useful as summarizing these 4 series and put them into one graphical presentation. Okay, here's when I put in 2020, and this is the outlier story. Employment took a great hit. It went up a little bit. Industrial production took a great hit. Income, it's not so far out of other potential outliers, but sales of companies took great hits as well. So this is going to cause problems in fitting. The Kalman filter is trying to subtly find changes in the data it's tracking. And these are drastic changes, so they can cause some problems here. Fortunately, the technique's all right. And here is 2020. So we do see the downturn coming from the 4 numbers, and we do see an upturn. And officially, the way that recessions are defined is they are the periods that the economy is declining, not the period that the economy is depressed. So we could even potentially, I'm going to be unclear whether the committee will now date the recession as ended at the bottom here of the green line. But we're only about halfway up from this great downturn. And we see in 2008, we had a downturn, and it took a while. It took over a year and a half to get to the halfway point. So we're almost at the halfway point, but we easily could fall again. We could stagnate here. It's not clear what you'd want to define that. But I don't think that's really the important point of whether officially this is a trough, a bottom point in the economy, or it's really want to know is the economy still suffering? Are people able to get out of unemployment? Are state budgets being able to improve and things like that? And so I believe that's going to take looking at COVID data, and I'll show some of this. And so the first thing before I started looking at the COVID data was I started to think about, I wanted to read about how do data scientists, not data scientists, but epidemiologists look at viruses and pandemics and such. And so they use a model that's been around since I think the 1920s. The most simplest form is called SIER, and it's called a container model. And so the idea is in your group, and this could be fish in an ocean, it could be individuals hit by viruses, it could be trees in a forest. There are N individuals, and there's a group that's susceptible. They haven't yet been infected, and they aren't immune. There's a group that's going to be infected, and they can infect other people. And then there's going to be a recovery. Sometimes it's called removed for R, but I like to use for this case recovered. And so these are now immune. So the way to think about this N population can start out as susceptible, move to infectious, and then become recovered. There are more complicated models, and actually most of the ones you read about, the predictions of deaths and such, come from something called an S, E, I, and R model, where the E stands for exposed. And so the idea is you're infected here, but you're not infectious yet, with the difference between E and I. There's also modeling that puts in who's been quarantined, who's been hospitalized. You can have death, of course, besides recovery. And then you can also allow this R to cycle back and become S again. So you could return to susceptible from recovered. And that's even possible in this modeling technique. So here I'll just show, this is easy to settle as a set, to solve for solutions by writing down laws of motion as difference equations. So you become not susceptible, I actually have a minus sign missing here, by some factor A times those that are infected. So every person that is infectious will make other people infected, and that's going to depend on how many they meet and how many they meet that can become infected. So this susceptible to the total population is very important. This is the change in those that are infectious, and this is the recovery. So these group become the recovery group. And so the most important here are these A's and these B's in these models. The number of contacts per day. We think of driving infectious behavior, and that depends. What's the probability? Not just that you contacted somebody during the day, but you interacted in a way that actually led to an infection. So if we have a mask on, the probability of just a contact relying in infectious will be lower. So this is a combination of two things going on. And the simplest way to look at the second factor B as a recovery rate is just take 1 over the number of days infectious. So for COVID, it's probably somewhere between 7 and 10 days where you're truly infectious. You can solve this in continuous time. I actually used a Python module to solve it. Makes nice graphs for me. But to use it with data, we need to turn it not from continuous time, but something discrete. But worse, all the data we can get is nothing like SINR. The government doesn't report, Johns Hopkins doesn't report, the New York Times doesn't report the S-force. It doesn't truly report the number infectious, and it doesn't report those that are recovered. And there's a couple different reasons for that when I show the data. And many people probably already know the details, that the numbers you hear on the news is not the number of people that are truly been infected or have been infected. Those are the ones that truly have been confirmed by some type of test by a lab. But most important, if we believe the model, it's this ratio of A over B that matters. If we have a very low B but a high A, that's really bad. So a low B is when you are infectious for a long period of time, and a high A is when you're meeting a lot of people and infecting them at the same time. So we also can have herd immunity. It's not just enough that this is high. There's a herd immunity that will go on. And actually this, I'll show a picture, it naturally goes down to 0, the number of infected people by some type of herd immunity. And if you know, there's almost nothing in this model, there's really no chance, little chance for intervention to lower the number of people infectious. And that's why you often hear this idea of all we can do is really flatten the curve. We can't change the number of people infected. But this is a simple model, and there are some work where people have looked at this A as changing over time. And we can think of people behave differently, and they could behave differently in different parts of the country, or even in the same states in different counties. They behave differently, they infect less people. Also, some counties, some areas are less dense, so you're going to meet less people and less of a chance for infecting them. So this could change over time. It could be very county specific. The B is probably fairly fixed. This is part of the disease. This is a simple picture of the model results. This is I in the red line. So it's saying that with some particular parameters, A set at 0.125, this is a 10-day infection rate, so A over B, we would interpret that as every infected person gets 1.25 people infected over the course of their 10 days being infectious. And so this is the new infectious, this is the stock of infected people, and this is S. And so we actually would say with these parameters, we get to herd immunity at about 36%. Changing the parameters a little bit, we get a picture like this. This is a less flat curve. We're still at 36%. Here's a highly infectious case where we're still 10 days, but you're meeting more people and you're getting 2.5 per infected person is getting 2.5 other people infected. And here it takes almost 90% to get herd immunity, but it happens quite quickly. It happens within 100 days. So this is some guidance for me of how I wanted to start this fit data that's available. To use it, give me some ideas. And so the data I'm using comes from Johns Hopkins. They're my main source. I actually use something that IBM has come out with through GitHub. They posted Jupyter notebooks, and I made use of those Jupyter notebooks to pull the data. I just simply run a routine. It takes less than 2 minutes to get a new harvest of data. And then I have my own data for the county level items. I have numbers like how dense is the population in the county, what percent have high school diplomas, what percent have college diplomas, what's the unemployment rate. I know some things about the demographics. I think I have over 300 items per every county in the US. There's roughly 300 counties in the US that I have items for. So this is a lot of information that I can try to put together. This is a aggregate of the numbers. Here we get this bad news that we in the US, as of the 14th of August, we had 165,000 deaths out of a population of over 328 million, and we had over 5 million confirmed cases. What we really care about is close as we can come to this I in the model will be this column here. So I'm just taking the difference between the reported confirmed cases. So the bad part about this, these confirmed cases are just when they were reported. They don't really tell us when the person was infectious, and they all have to be confirmed by a lab test. So they're not a doctor noticing the person has lost their taste or has other symptoms that are something you would tell us for. So some of the estimates are that this is probably by a factor of 5 to 10 too low. And that tells us these numbers are probably by a factor 5 to 10 too low. So as best we can do as modelers is somewhat assume that the ratio of actual infectious is proxied by the change in the confirmed. And here I've just divided it by thousands. So this is telling us right now across the US, at least as of the 14th of August, 1.1 per 1,000 people were infected over the prior 7-day period. So I just take from Friday to Friday, and the reason is Saturday and Sunday reports are quite low. So it's just Friday to Friday numbers. Population, I'm assuming, stays fixed. Here is what I say is we should be looking this on a county by county basis. Here I just have 5 local states. This is the level as of middle of August for, and we see that New York is the worst. So this is roughly, these numbers here in red are roughly these counties here have over the course of the disease has seen about 25 people confirmed with COVID per 1,000, and that's pretty the high point. These are almost zero. So there's some parts of Pennsylvania that are quite low, and this is the idea of counties. There are parts of New York here that are much closer to Pennsylvania than they are to New York City. Here's parts of Delaware, I guess is shore behavior again. This is outside DC, this is Maryland. So this is the level, and here's the change. And so we get a much different picture. This is the level over a long period of time, and this is the last week. And so we see much bigger outbreaks relatively in these counties compared to other counties. One reason why these might be low here, especially in New York, these are new potential infections. They have a little bit of herd immunity going on, or they have more social distance where their A is lower than in these counties here. So this is why I was in charge of the news. We want to report per 1,000 people infected by county, not by how many people, how many millions in the whole state. So if you want to worry about somebody infecting you, you want to know what are the odds that that person from this county would actually be infected, and that's going to depend on the new infections per 1,000 people in that county. Let's see a couple more pictures I can show. So I did some simple data fitting. So my dependent variable I'm looking for is the change in COVID per 1,000. I try the lag of the same number, the lag of the level, density of the population, population with high school diplomas, maybe they are less likely to worry about this. Median household income, if it's higher, you think that you would have less chances, you have better medical care. And we might not be clear about whether the unemployment rate in 2019 would cause higher or lower. The idea would be if an economy is booming in a county, everybody wants to be going to work, earning money, and maybe that would increase COVID. Or if the unemployment rate is low in a county, they might be more careful about keeping their jobs. It's not clear. So my first look at this simple linear model in a panel structure, almost everything works. I have 3,000 observations. I have 17 weeks of data. And so almost everything seems to be statistically significant, but I'm not fitting much of the data. I'm only fitting about a quarter of the variation in this change here that I'm looking for. And so that's not really sufficient to understand what's going on. And so working with my colleague, we're going into looking at regimes. The idea is that counties that are close to each other are counties that have population very similar, are counties that are similarly dense, or counties that are similarly rural, maybe in the same regime or the same behaviors. Not sure how many regimes there should be. So the Dirichlet process is probably the best tool to use. I won't go much into that. The simple way to think of Dirichlet process says that there's a random process that pulls from a random process. So it's a double random process. And then we use some Bayesian priors. Because a lot of things are unidentified, it's really good to kind of shrink and use this idea of other information. This is something I didn't want to, I won't have time to go through and cover very much about, I won't have any time to cover it all, about the Bayesian ideas, the descriptive. But here's the simple ideas, is I've written down 81 possibilities here. So you could have an economy that's open or a county that's open, partially open, or closed. You could have a low number of cases in your county, modest number of cases, and a high number of cases. You could be rising, you could be steady, you could, oh, this should have been falling infection rate. You could be recovering your economy, you could be holding steady, and you could be doing a retraction. So we think about these regimes as drawing from any of these 4 boxes, and each of these boxes you would choose from. Some of the difficult part is we really don't have a good idea of what it means to be open. We might not have a good idea of what it means to be modest versus low. We don't have a good idea about what it means to be steady versus rising. And we don't necessarily always have a good definition of what's the difference between a recovery and stagnation. So we're going to try to let the data do this. This is the descriptive process does this. We have potentially 81 clusters because we'd have all these possible combinations. We believe it'd be much less than that. So we're just getting started. And so the idea is to have the economic recovery, we're going to need low cases and at least steady before we get an economy recovered. And then we have to also worry about special cases. We're going to have college towns that are going to dominate some counties. Even, football is going to, the loss of football in some counties, Penn State, for example, in Center County, is going to be hurt greatly by not having tailgates and other sports and things like this. And to be more county by county special cases. So summarizing everything, we're just mostly doing the setup work as I'm taking suggestions, gave me a chance to put some of my ideas together, give me a chance, thank you for talking them through. So we're going to be combining economic indicators and COVID cases. We have to recognize that almost everything we need is completely unobserved. We can't even ask people what's happening. We're going to need nonlinear models. Let me jump back a little bit about the nonlinear models. And then our goal is to find commonality in county patterns because everything is observed. And so I'm going to jump back. I forgot to talk a little about the nonlinearity. This is the nonlinearity issue. Is we can't simply expect one ordinary least squares or weighted least squares or anything to fit this red line here. It's going to rise, it's going to fall. It's not going to follow any nice pattern. So we're going to need some better techniques than the Kalman filter or ordinary least squares or panel data type of work. So again, I'm just summarizing. Well, I want to go further than this, conclude. So just some tips in doing work like this. I want to use all my tools of coding, management of data, math, statistical theory, and any type of area expertise, including I'm speaking to many people about the epidemiology, which I sort of came into this only 6 weeks ago, knowing almost nothing. I also wanted to understand some of the basics. I myself knew the Kalman filter, but you might want to look that up and use that. I had to learn the Dirichlet process was not part of my wheelhouse, but I don't reinvent the wheel for things I don't have to. For example, I used that IBM set of notebooks to harvest data. But I did want to understand the data and how it fits in theoretically. I also worry about the best form. So I used a ratio of change in a number divided by population. That was the best form. But there's many different decisions I could have made along these lines. And also I'm going to care about relevant variation, such that I'm going to get variation by looking at counties. If I had aggregated everything together, and went back here, this is not going to be enough variation across the nation to understand what's going on with the COVID cases and the economy. So thank you. I'm done with my talk, and I can take any questions if you'd like.
All right, thank you very much, Michael. That was really interesting and definitely a very timely talk. So we have a couple of questions that came through. The first one is basically regarding, you talked about the difficulty of getting the data. And somebody posted, I read an article about an economist using alternative data because of the rapid deterioration of the economy and the lag with some typical economic indicators. And she's curious to know if you considered using alternative data to fill in the gaps, or if you have thoughts about using alternative data sources such as number of flights, restaurant reservations, etc.
Sure. Those are all good ideas. Where's back to my data? Am I showing still my slides? Yeah, my data.
Yes, you are.
These are all conventional. So there are some less conventional. ADP, what is ADP? Auto something, I don't know. They're a payroll company. ADP has numbers that probably can be used as well. I know some other research has used GPS data coming from Google Maps. They can actually watch people move. And we've also seen things like that. Flights would be another one. Yes, all type of information like that. The flight one probably won't fit into my county idea too well, except that counties that have airports now are going to be hurting more than counties that don't have airports in a relative term. But yes, we're going to have to be much more creative. I probably should have had a whole slide of creative data sources. Unfortunately, many of those data sources haven't been gathered historically. They're not as well understood, but economists are trying to get more creative here.
Okay, thank you. And then Casey wants to know, can you talk more about your concerns over federal statistics such as GDP and what you think they could be doing to improve? Or join the 21st century, as you put it.
Yeah. So if I was in charge, wouldn't everybody tweet in the morning, am I going to work? That would give us the unemployment rate the next day. Those are the type of things we could do. So the number of people that are measured for the unemployment rate is roughly 0.1% of the economy. The payroll employment is much closer, but still what they have trouble with is the death of companies. So when they don't get somebody from their payroll saying that no one's working there, immediately they don't know whether that company went out of business or they fired everybody. And those are some of the problems. So most statistics have been gathered with ideas back in the 1980s with mainframe computers. There's a statistical analysis procedure, now it's known as X13. It started out as X1 all the way up to X13, and it's way obsolete. It's not what you should be doing, but almost all economic data from the US comes out with the X13 method. What's some more other ones? GDP, if you know, there was a great problem with GDP. It was only the problem in the first quarter. They were getting the seasonal adjustments wrong every first quarter for about 8 years straight. They finally straightened it out, but it was kind of ridiculous it took them that long. The other one I would really like changed is unemployment insurance claims. Those should come out by county, and they should be out, well, they come out about a week late. That's pretty good. So they're very timely. They're nice because people make that decision. They qualify for unemployment insurance. They want the check. It's not as simple as, am I working or not? That's sort of you're trusting the person's word. So these are, show me the money type of statistics. And it would be nice if these were more geographically diverse. The fact that the U.S. does a 10-year census is just nuts. And that's all because of the Constitution. There's no way if anybody's in charge of looking at our population, you'd only make a measurement every 10 years. We do something called American Community Survey, which is close. But again, there's almost nothing the government does that looks like the 21st century. There's nothing that looks like open source. They're using COBOL programmers, things like that. That might be, I'm going to get myself in trouble.
All right, thanks. And then Rama wanted to know what are the different types of clustering that you've considered in addition to Dirichlet clustering?
So there are some other methodologies we've looked at. So you could use some type of logit model clustering, some other things, but the Dirichlet is probably the most amenable to Bayesian ideas, and that's why we're using it. Okay. We have not even solved the programming part of the Dirichlet process. So there's a lot of packages that will do this Dirichlet Bayesian, but they're really for univariate. They're not for fitting the data like we're looking at. But it's close. So we're still working on, we're using R or Python modules. I found a very nice Python module I'm learning that'll let me do the descriptive parallel processing, which we really need. So what we're doing right now, it probably takes 2 hours to come up with something, and that's not going to work.
Okay. And then the last question that I have here for you is from Philip, and he wants to know, do you think the small gap between unemployment and recurring unemployment is significantly impacted by the $600 government contribution?
This is this picture here. We see it?
Yes.
Yeah. So the theory coming at least from the government statistical, they're not. I think their tools are hard to work with. So they're pretty smart. Their belief is the household survey people go around and ask questions, and a person can give one of 4 answers. And one of the answers they're tending to tell people is they're employed but absent, meaning their employer just doesn't want them to come in this week, or they're sick and they're afraid to come in. And at the same time, they're applying for unemployment insurance. So it has something to do with that, but they really think it's a problem more with the blue line as opposed to a problem with the yellow line. So if you're unemployed, and whether you're going to get a $400 check or a $600 check or a $1,000 check, you want the check. I don't really think I can guess that it's the size of the check that really drives it, but we really think this blue line is too low. So a lot of people are reporting as absent because their employer is not really being clear. They are still allowed to apply for unemployment insurance in those cases if you are indefinitely laid off. If your employer says you're coming back in 2 weeks for sure, you usually cannot get the unemployment insurance. So it's more of a, I think it's more of a blue problem. There was a recent study that came out and said some things about, is the $600 extra stopping people from coming to work? And they said no. I think they got it wrong. It's clear that if you get this extra $600 and you would have to go and work at a restaurant and could get sick, I gotta believe many people are taking the extra $600. But it's more of an opinion. So the quick answer is the blue line is probably more of the problem than the yellow line.
All right. I know I'd said that was the last one, but I'm going to ask one more and then I'll just open it up. Anyone else who's got questions can unmute and ask. And Sid Misra wants to know, is there an opportunity for an unsupervised model to look at the behavior of counties that have maintained a low A to B ratio, i.e. fast recovery rate and a low infection rate?
So I don't think I'd call that unsupervised because we still have a target we're going for. We're going for infection rates going towards 0 and deaths going towards 0. So I wouldn't necessarily call it unsupervised. We could do unsupervised learning to group counties together by these 300 some variables I have before I saw the COVID. So that could do some. So we might have to, I'm going to think about that. That's probably a good idea, is to start to group the counties pre-seeing the COVID numbers. So I think there's something there. So I have about 300 attributes for the 3,000 some counties. And I could use some type of unsupervised learning to put those together. Yes.
Okay, thank you very much. I am going to open the floor now, and anyone who has any additional questions for either Michael or Andrew or Ben can go ahead and unmute themselves and ask. Thank you so much for your talk, Michael.
And I should unshare my screen. Is that the right thing to do? Yeah.
Yes, that sounds good.
I know how to do
Michael,
that.
I have a question on the very slide you're showing.
Oh, okay. So I'll keep that.
So,
okay, yes.
So when I'm looking at this, right, if we see that the unemployment rate is spiking so much in 2020, so wouldn't we assume that, I mean, I would expect rather that the red line, the initial claims also would follow that, not that the continuing claims would increase, right? Because if somebody was, my understanding at least of continuing claims would be like, even previously they were unemployed. And so they're continuing to take that unemployment. So those were the people who are not like specifically affected by this, the pandemic. But then the red line is where I would assume would be the one that's closely following the blue and not the yellow one. Any thoughts on that?
No, it really should be the yellow and the blue. Let me try to explain that well. So in spiking purposes, here's the spike in initial claims. So initial claims tell us something new in the economy, and the continuing claims just carry that on. So if you're unemployed and you want to get unemployment insurance, you first are always an initial claim. You make your initial application. That measures the initial application. I believe you get the check, but then your employer could fight you over it. And they could claim you just didn't come to work. You don't deserve to get unemployment insurance.
What are you doing? What's the 15 minutes?
I have to put them back in.
Oh.
And then you could be thrown off. So you are always an initial claimant. You become a continuing claimant, and you leave when either you age, when you number of weeks you age out, or your employer fights you over it. So the continuing claim is like you are still unemployed. So this blue line comes from the household survey asking individuals to put themselves into one of 4 boxes. And the boxes are you employed and working? Are you employed but absent for some reason? You could be absent because of a snowstorm. Are you unemployed and looking? Or are you unemployed and don't look at all? So those are really the only 4 categories. And they're closer, the yellow and the blue are closer concepts.
You can also come off from getting another job.
Yes, so you could leave the yellow by getting another job. Yes, yes. So there's 3 cases, you're right. And here's things to know is the amount of people every week that ask for initial claims is tremendously high. It's like almost 1 million a month. And the unemployment number is closer to about 6 or 7 million. So there's much bigger flow in initial claims than levels. Levels are kind of steady, but initial claims are all over the place. And they would say they're like the news and the information in the economy. That's why I would like to see it more geographically diverse.
New topic, Michael. Curious on the population. I noticed your population didn't go down with deaths. And,
yeah, that's laziness, not laziness, but yeah, this is my slide here. Yeah.
Curious, do they account for tourism? I mean, is that a significant number? The people that are in the country. I mean, does this have the students who are here on a visa, or is this all just citizens?
You're asking about the 328 here?
Yeah.
Yeah, so this is actually gathered a year ago. This comes from the 2010 census populated forward. So the good numbers coming out from the Census Department are roughly every July. So they're the July level. That's roughly what this number is. So it will not get deaths. It's about it, but I want to normalize it by something. I don't want to compare Broward County, Florida, to Warren County, Pennsylvania, right? So that's what I want to.
But even with that, you're working with citizens. You're not counting people out here on visas and tourists.
No, it's more than citizens. It's the official definition. So what do they call it? It's more. It's everybody. It's the number that goes with what they will put out in the 2020 census. If you are counted in the 2020 census, you're potentially part of this. So it is the 2010 census projected forward by county to 2020 until they get a new set of numbers. So it's everybody they possibly could count. You're a living person. They do not throw you out for any reason.
Right, but that still wouldn't have visas.
I think it's a good question. I don't think they ask you. They will ask you if you live in a different place. So if you're a college student, you should be measured in where you consider your true resident. But you could say it's this dorm, and they would count you for that. I believe that's true. It's whatever the definition is of the 2020.
All right, thank you.
Just a quick one. That's sort of like some of these numbers are hard. We want to count long-term facilities, prisons, and things like that. But, you know, we just can't get those numbers. So a person is, yeah, this is a person here by no other separation. Okay.
So Michael, I have another, this is Rama here again. I have another question for you.
Sure. Mm-hmm.
I mean, this is a very interesting study. I mean, it is very significant, and I'm sure it'll be very helpful to the local communities, the local governments, to see as to, based on this model, like, you know, as to how the recovery is or what they can, you know, at least plan out for in terms of economic recovery and all. I know you said that this is still a work in progress, but if you, I don't know, based on your timeline or anything, do you have any plans of making it like an app that is available that the local governments could use, and then it's based on the data itself in that county, so that may be something that's super helpful for them?
I'm more likely just to stick with the GitHub model and let anybody else build an app from the data I'm gathering up. What did I say? So the true data I want is 6 months away, unfortunately. So for every county here, in another 6 months, I will know their June employment by major sector, like restaurants, healthcare. So I don't have to worry about surveys. We will almost have a census of every single county's employment. And that's really, so it's going to be about 6 months till we get the data we really want to understand what's going on. But we can believe that as long as the COVID, and that's sort of the confirming hypothesis here, as long as COVID is important in the county, that county will not come back in the full sense. Because people will not be going to restaurants, they will not be traveling around, they will not be doing a lot of things that we would record as regular economic activity.
So Michael, for fun and profit, did you look at the economic model in relative to the stock market rather than to the economy?
No, the stock market is going to be harder because it's national. But I would say, let me see what I could say there, is that if I had given my original talk was, when are we going into recession? It would be after the unemployment claims spike and the stock market falls. So we always know the stock market falls before a recession. That's been clear. It's not clear the other way around. Do we get out of recession just because the stock market rises? That's not as clear. And it's not clear that the stock market rises because the economy is doing better. It'll also rise because maybe interest rates are falling or other effects are going on again. So another way, in a technical sense, you would say that a rising stock market is not sufficient for a expansion, and an expansion is not sufficient for a rising stock market. So you still have to do your gambling there. The only thing I would say is I hate Robinhood, right? That has to be the worst idea ever.
I'm sorry, which?
You know, this Robinhood app that encourages people to every day bet on the stock market. It's like the worst idea ever. So if you took this to the extreme, you would follow the COVID data and then use the Robinhood app to bet on the stock market. It's a way that, if you look it up, it's an app that the average person can use a stockbroker for cheap.
I'll take a look at it.
But I don't like the idea, and I don't think this is the getting rid of COVID is not going to be sufficient for the stock market. We are going to get a massive number of bankruptcies in this country, especially from small businesses, and that's going to have a massive effect on small banks. It's going to have a massive effect on commercial real estate.
Oh, good, thank you.
Nice scaring everybody, sorry.
But the same techniques, the Durlash, you should be able to use that in
I see what you mean. I see more what you mean. There are clustering techniques that have been applied to the stock market. You're right. I've never seen the Durlash process being used. I haven't thought about it enough at all. But there's no reason it couldn't be used. But there are without a doubt that people cluster the stock market. They'll look for growth stocks versus value stocks. They'll look for small cap versus mid cap. And so those are a type of clustering as well.
Thanks.
Okay, thank you very much. I think that wraps up our Q&A session. So I'm just going to stop recording at this point and I'll hand it over to Rama. Thank you.